Okay, hello and welcome. Just take a moment to let's get the take a moment to get the audio here going. Pop out the chat. Going. Hello. Pop out the chat. Going. Hello. Very good. All right, so get right into the next question. Decided today I'm going to spend some time on LeetCode again. Not sure what I want to do exactly. I could take a moment to chat about. So, yeah, I have some difficult things in my personal life. I'm not sure exactly what direction to take, what to do. I'm figuring it out, working on it. But I have some significant challenges to deal with. Today I'm just going to do more LeetCode because I've got thousands of questions to go through. So it's okay for me to spend time on this every now and then. I'm not sure what to do. I can kind of just do these problems. But yeah, there's like a ton of other stuff I need to work on. It's complicated. It's really complicated. But I'm learning now what some of the problems are that I've been facing, what I've been dealing with, and why things have been very difficult for me in my life at certain points. What it is and what it has been and all of that. We'll kind of take things one day at a time. But for now, we'll just do I'll just spend the day solving these questions, and I'll come back to my other things I need to do. I could do those things at another time. Don't need to do them right now. I could do them a little bit later. All right. So, oops. What is this? Oh, yeah, I saw this one before. Oh, I see. Okay. Right. So let's keep going. So maximum tree is a tree where every node has a value greater than any other value in its subtree. Excuse me. It's like a heap. You're given the root of a maximum binary tree and an integer val greater than any other value in its subtree. It's basically like a heap. Just as in the previous problem, the given tree was constructed from a list. Root construct A recursively with the following construct A routine. If A is empty, return null, otherwise let A of I be the largest element of A. Create a root node with the value A of I. The left child of root will be construct A0 to A minus 1. The right child will be construct A plus 1 to A.length minus 1. Return the root. Note that we're not given A directly, only a root node A construct A. Suppose B is a copy of A with the value val appended to it. It is guaranteed that B has unique values. Return construct B. Example 1. Input root 4, 1, 3, and some null values. Value is 5. And then output should be 5, 4, 1, 3, 2. Explanation: A is 1, 4, 2, 3, 3, and B is 1, 4, 2, 3, 5. Is this a host order traversal? I don't know how the arrays to tree, what do you call it? The array to tree functions, I guess, or mappings are not so obvious. Number of nodes in the tree is between 1 and 100. The values between 1 and 100 inclusive. All the values of the trees are unique. Values between 1 and 100. Oh, I see. Okay, inclusive. High acceptance rate. Okay. I don't really know what I'm looking at. It's like a lot of words and kind of hard to follow. You're given the root of a maximum binary tree and an integer value. Okay, so kind of a heap. The given tree was constructed from a list with the following construct routine. Note that we're not given A directly, only a root node. Root equals construct A. Okay, where A is the array. We're not given the array, we're just given the tree that results from this array. Okay. Suppose B is a copy of A with the value val appended to it. It is guaranteed that B has unique values. return constructive B. Okay, so basically, oh, I see. So suppose we have this array, and we append B, and we can construct. So okay, I mean, there's a few ways to do this. Number one, you could figure out a way to go from the array back to the tree, or excuse me, from the tree to the array, append the value, and then go back to the tree from the array. So you can go array to tree and then tree to array, or excuse me, tree to array and then array to tree. You could do it that way. That's one approach. But this is probably easier than that. You probably can go straight from tree to tree, is what I'm thinking. It's not so obvious how to do that though. So if obviously if 5 is larger than everything else, you could just make it the parent. A of I be the largest element of A. Create a root node with the value of A of I. The left child will be everything to the left. Right child will be everything to the right. Okay. It's not exactly a heap. It's a kind of a special kind of heap, where the heaps usually you want to have a you want them to be height balanced. This is basically not a height balanced. It's a heap that's not height balanced. Is kind of what's going on here. So what's interesting is that it's not clear where exactly this new value should go into the array. Yeah, you could try to insert the node into the tree. That's one approach. The other approach would be to try to take the tree and recreate the array and then just run through the array to recreate the other tree. That's another approach. Obviously, it would be more efficient, I think, to just insert the node somewhere. I don't know which one's easier to think through or to code, though. I don't know. I have to think about it. Which one's easier? It's hard to tell immediately. Okay. 5, 2, 4, 1. Val is 3. So 3 ends up to the right of 4. Okay. And then 5, 2, 3, 1, 4. 4 ends up to the right of 5, but the parent of 3. Okay. It gets inserted here. Larger than 3. Yeah, it's not really obvious where the node should go. So one more time. So it could. So okay, let's say we insert it into the tree, right? Let's try that. We could say it's larger. It's further to the right than anything else, right? So anything that it's larger than, it's going to go to the left. So it's larger than everything, then the whole thing is the left subtree. Let's say it's smaller than this node. If it's smaller than this node, what is that? That means it has to go to the right. And the reason is the right children are all values that are further to the right, right? So if it's smaller, it's going to go to the right subtree. If it's larger, then it becomes the new root. If it's the largest, if it's smaller, then it becomes go to the right of this node. And that means that this would be the parent, potential parent, and it's going to be on the right side, and then this what is on the right side could be the potential child. And so in the case of where there's a 3, right, 4 is to the right of 5, so it goes down to the right, or excuse me, 3. Or no, let's look at this one. Yeah, 4 goes to the right. It goes to the right because it's smaller than 5. But it could be larger than 3, in which case this entire subtree becomes the left child of 4, because this is to the left of 4 means it's here, right? The left child has to be these smaller values, smaller indexed values. And they're also smaller values too. So you end up with this kind of a picture. Let's say it's smaller again than 3, that's sort of here, right? So let's say we put 3, it's smaller than 5. We go to the right, it's smaller than 4. We go to the right again. Whatever it's larger than, that becomes the left child. That's kind of what happens. So we could do it that way. I think that works. It should be linear time. Could just use a simple for loop. We'll say P, this null pointer, current equals root, and then child equals null pointer. And we'll say left child, right? I don't actually know if I need the left child, believe it or not. I think I just need the parent. So it's going to be while current and current. So the idea is how does it work? It's you're going to go down the right side. If the right child, you're going to stop when the right child is smaller, right? And current right val. So we have current and current right and current right val. Excuse me. Is less than value, or no, is less than value. Yeah, well, you keep going if it's greater than or equal, it's greater than the value. I think all the values are unique, right? Yeah, we don't have to worry about that part. Yeah, so let's see. The parent is set to current, and then current is updated to the right side. Okay. So current, no. Current is that node. It's not going to go current right. We're going to just say current is that node. Keep it simple. So check the current node against the value, and we're going to stop when that current node is larger. We're going to stop when that current node is smaller. Excuse me. Yeah, keep going. While that current node is larger than the value we're trying to insert, we're going to keep going. Okay, we keep going down to the right. And I think that's all I need to do here. Once this loop is completed, we have a parent, which is the previous node that we came from as we go down. And there are two edge cases, right? There's no, it could be the root and there's no parent, or it could be a leaf and there's no actual current node. So we say if current and not p, we do one thing. If not current and p, we do another thing. And then finally we have one more. And we can say tree node result return or result. So if we have the current value but no parent, that means we're at the root node, and that means we've got to set create a new tree node. Let's say T. Let's do it that way, actually. Never mind. T. I'm going to create a new tree node no matter what, actually. So That always happens, right? We're gonna say t left child is gonna be the root. So there's no parent. That means the root becomes the left child, and we set the result equal to t. Next, we say if it's a leaf, in other words, current is empty, but there's a parent, then that means we went all the way down the right side, and this value was smaller every time, right? Maybe this should be better. Val is less than current val. The value is smaller every time. That means it's actually to the right, an index, which means it's got to be. Yeah, that means it actually goes to the right child of P. So P right becomes T, and result equals root. And finally, and this actually should actually just be the root, typically, I think. Finally, current and P both exist. We're going to say the parent right child becomes set to T, and T's left child becomes set to what was the right child of parent. And then the result is still, yeah, it's a little bit confusing, but yeah, there's a little bit of sort of node manipulation there. Oh. Sometimes I forget to put my pointers up correctly. Okay, so I think this is it. I'm gonna just go for it. I could be wrong, probably wrong, but I'm just gonna go for it. Oh, got it. Sweet. Yeah, there you go. 100%. It's very good. So I'm gonna submit that like 5 times. Yeah, it took me a while. It's 17 minutes, 18 minutes. Submit that like 5 times, and then we'll go to the next question is we'll go to the next question. I'm gonna stop the stream and restart it for the next question. I'll do it that way. 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, and submit it one more time. That'll be that. Okay, very good. So yeah, if you like the video, don't forget to like and subscribe to the channel. All right, take care.